All right. All right, so let's start these hands-on ones starting down here. The first ones just demonstrate the capabilities of machine learning models, and all these involve coding in Python. You could use any Python environment, but I like Google Colab because every student has access to it and you don't need anything special in the way of a computer. You just go to colab.research.google.com with a Google account, and they will give you a free virtual environment to run Python in, which is very powerful, and you can't argue with free. Now, you cannot run long processes. It'll only run for about an hour or an hour and a half before it hangs up on you. But anyway, so now you can make a new notebook, and there it'll load up a container like a virtual machine, and it gives you an environment to just write code in, and you can just execute Python code. And this is what I'm going to use. Um, it's very good for all my programming classes. So the first one here is basic machine learning to see how it goes. So first we're going to import the TensorFlow library, which is one of the more common ones used for machine learning. So I just import it, and let me zoom in a little bit here. All right, and then I print what version. So here it is. It's creating an environment for me, connecting, assigning me some processor and RAM. That takes about 30 seconds. And here we are. I've got a about 1 GB. I got 12 gigabytes and 100 gigabytes of disk space to use just for me in my container. And there it has imported this thing and found what version of TensorFlow I have. I don't care what version, they're all fine for what we're doing. Okay, so now let's give it a problem. So suppose I measure something like X and Y, like the pressure in something versus the temperature. And here's the answers: -1, 0, 1, 2, 3. And here's the Y: -3, -1, 1, 3, 5, 7. So this is the kind of science I did for years. You measure something, then you try to guess what the relationship is. Well, pretty soon you notice when X goes up by 1, Y goes up by 2. So this is Y is 2X plus 1. Now that's what a human does. A human looks at this, and because of human intelligence, we're able to deduce a pattern. And so the machine learning is going to figure that out without a human having to do it. Instead of having a human program in this equation, the machine is going to learn that. And it only takes about 10 lines of code to do it because, of course, the reason Python is so easy is because other people have done all the work by writing libraries. And all we have to do is learn how to use their libraries. So we import TensorFlow, and then this thing called Keras is an easy machine learning library. So we make a sequential machine learning model containing one neuron. And then we use standard measures of loss and standard measures of optimization to fit the best curve to that data. And here's the data, X and Y. So let's run this and see how it works. There's the code. And so when you run it, it imports some stuff. These are the import. And so now it has epochs going by. What's going on now, this is the standard way you do it, stochastic gradient descent, SGD. You have a model with some parameters, and you just start them with random values, and then doing partial derivatives in all those variables, you figure out what direction would cause the loss to get smaller. And you take a small step in that direction because the partial derivative assumes that it's linear in all the parameters. And of course, things are linear for small steps, but for larger steps, they would curve. That's why it takes a little step. So the loss here is the mean squared error. It takes the error between the model prediction and the actual observed Y value and squares it and adds that up for all the points. That's the mean squared error. So the loss is 2.7. It takes a little step, then the loss goes down to 2.2, goes down to 1.9. By taking a whole lot of little steps, it's just like a ball rolling down a hill, trying to find the bottom. And so it takes 500 steps. And as you can see, the loss just keeps going down and down. And after a while, the loss will get very small indeed. If I get down to epoch 500 here, the loss is now down to 10 to the minus 5, which is almost zero. And then to see how good it is, I just printed the prediction for an X of 10. And the right answer is 2X minus 1. So the right answer is 19. And as you can see, it's 18.98. So it got very close to fitting. So that's fine. That's how it works. And here's my model. My model is X comes in. It has one neuron that just does a linear function on X and mx plus c. So there are only two parameters, m and c, and it's trying to find them. The right answer is 2 and minus 1. And so if I program this again and print out the actual values that it learns, we'll see how close it got to 2 and -1. Those are the weights, the parameters. So I'll just make that model converge again here. And there we go, doing 500 steps. And the loss is falling down, 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 as it should. Run a little slow, but it doesn't matter. Actually, a lot slow, which is strange, but maybe the Google is running out of resources or something. There, and so here's what I learned. -1 and 2. 1.99 is how close it got to 2, and -0.99 is how close it got to -1. So in this simple case, it gets very close to the right answer, which of course is what you'd expect. So that's fine. Now let's try putting some errors in the data. The data there was perfect, so in principle the loss could get all the way down to 0. Let's see what happens if I give it some realistic noise. Now instead of y being those numbers, I just added some random alterations to them. And I guess I'll comment out the first one. It's not necessary, but it looks cleaner. Now I got 3.1 instead of 3, and so on. So if you give it data with some noise in it, now the loss is really big, like 28. Now it goes down to like 1. Remember, before it got down to 10 to the -5 after 500 epochs of training. And this time it's getting out of 0.005, and I think it's only going to get down to like 0.004. That's as low as it can get because there's noise in the data. You can't get the loss below a certain level. So here's what, it ended up with a much higher loss, but again, it found 1.99 and -0.99, so it got very close to the right curve, fitting the best curve through those points. So now, what happens if I try to use a parabola, x, which is a curve, and a straight line really won't go through it at all? It will still try to find the best straight line. And this is why, and it may be obvious that it will do this, but this is essentially what's wrong with the large language models we were using yesterday. It's fitting a mathematical function through the question, and even if the answer doesn't make any sense, it will still find an answer and show you the answer, and it will look good. It just won't be a good representation of the truth, because the model doesn't understand the truth. So here's the loss going down, 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 trying to fit a straight line through a curve. And the loss never gets very small at all. Remember, 10 to the -5 was perfect. 0.004 was a normal thing, plus data plus noise. Now the loss is 4. So it's finding the best line that goes through that curve, but it's a terrible fit with 4. So it's it found numbers of -0.7 and -5 for the two predicted values. It's fit some kind of line through there, but it's a terrible fit. And now let's try fitting a more complex curve. We've just done one neuron in a straight line. So let's have a more realistic model where you feed in X, then we're going to have a hidden layer of many neurons, each one of them taking that data, and then another hidden layer to do a second layer of processing, where it takes the output of all those neurons and processes them again, and then goes to an output layer. This is the way real complex situations are fit. Now you have a lot of parameters. Each one of these junctions has 2 parameters, a slope and an intercept. So for that, you have one linear layer going in, then you have 64 units in the first hidden layer and another layer of 64, and then an output layer of just 1. So you have one input X and one output Y, but in the middle, you have a whole network of neurons. So we're going to display the model and then train it and print the output, plot the output so you can see it. And to give it data, we're going to give it a nice curvy thing. We're going to give it 0.1x cosine x plus some random noise. So it's going to fit a more interesting curve. All right. So here we go. This is what the model is. You have one input neuron, that's 2 parameters, slope and intercept. Then you have 64 in a first hidden layer, so that's another 128 parameters. Now you have 64, and each one of them gets input from all the previous 64, so that's 4,000 more parameters because it's something like 64 squared. Then you have an output neuron where all those 64 go into this one, and that's 65. So the total number of parameters is now 4,355. Whereas before we only had two parameters when we had a model with only one neuron. So this could fit a really complicated curve with all those parameters. So now the loss is 0.4, the loss is going down. It's going through its steps to go down, down, down. And when it's done, there's the graph. The dots are the input data, and the red line is the prediction. So it's working pretty well. With 4,000 parameters, it ought to be able to fit it. By the way, also notice it didn't do overfitting. If it did overfitting, it would try to spike every data point going up and down. But this is doing what you hope it would do. It's getting the trend underlying the population, not the noise of your specific data. It's not perfect, but it's pretty good. All right, now you can now play with it. So suppose we wanted to remove one of the layers. Instead of having two layers of 64, let's just have one hidden layer of 64. That's easy to do. We'll just comment out one of these lines. That's going to make the model much simpler and smaller. And so if you run that one, now it has two parameters here, 128 in the hidden layer and 65 there, so it only has 195 parameters instead of the 4,000 we had last time. So you would expect it to be much faster to compute and learn and a whole lot less precise in the fit. And however, it's still pretty good, but you can see it's getting a sort of rough approximation. It's not really following the dots here, but it's getting there. And so you can try various versions here. And there's some flags defined by just trying various combinations of hidden layers and units per layer to see how they all work. And then you can vary the amount of input data and vary the amount of noise. Like I wondered why you have 1,000 points to trace out that curve. It looks like you really don't need 1,000 points to trace out that curve. I think maybe 50 points should be enough to trace out that curve. In practice, it's really bad if you have a lot less data. And that's another fundamental thing about machine learning. You need a lot of data. That's why people already are running out of data on the internet. They've trained the existing models on basically all the text you can find on the internet. And they say the real valuable properties, where are you going to get many terabytes of real text written by humans anymore? That's why Elon Musk thinks he's ahead because he has all the text on Twitter. And Facebook has all the text on Facebook, and they're starting to charge money for that. Reddit just sold the rights to train on their data to OpenAI. Anybody with a large corpus of data written by actual humans is now seeing that as like a valuable gold mine because you need a lot of data. Anyway, so this gets you started with fundamental machine learning. I'm going to stop this video.